would like to welcome our two co-chairs for the US CLIVAR Working Group on the Changing Width of the Tropical Belt, Kevin Grise from the University of Virginia and Paul Staten from Indiana University. So thank you for taking us today, and I will let Paul get started.
Thank you, Kristen. Thank you for arranging this and getting things started. Thank you, everyone, for taking the time to tune in and participate today. We are the US CLIVAR Working Group on the Changing Width of the Tropical Belt. I'm Paul Staten. I'll be starting us off before passing the baton to Kevin, who will get you caught up on what portions of our working group have accomplished. When you hear tropical belt, I think sometimes the first thing that comes to mind is rainforest and coral beaches and things. And when we're talking, our working group is generally talking about what I think of most people think of when we think of subtropics, so the dry belts on either side. So if you look at this almost obligatory photo from Apollo 17, I mean, it reveals large-scale cloud organization and vast expanses of clear skies. And for background, for any of those not focused on atmospheric sciences, these are broadly organized into bands. This is typical for rotating atmospheres. So near the equator in the deep tropics, you have pockets of cumulus clouds with loose organization. Then on either side, you have your mostly clear skies associated with many of the world's deserts, several of which can be seen here: the Sahara, the Syrian, Arabian, the Kalahari. And then further poleward, you have your more organized storm systems typical of the mid-latitudes. These climate bands can be described in broad brushstrokes as with a three-cell model of the Earth's circulation. So you have strong insulation near the equator, resulting in low surface pressure, rising air. The cumulus clouds known previously, this rising air produces clouds, releasing latent heat. It diverges aloft and moves poleward before it begins to sink. And that latent heat it gained earlier is manifest as warm, dry air in the subtropics, typically. In the Eulerian mean, this is about 30 degrees north or south. And because of the Hadley cells, the circulation, the Hadley cells' domination of tropical climate, it's often used either as a metric or even sometimes as a definition of the tropics. But lately, the width of this circulation pattern and of tropical climate zones has been increasing. This was first noted looked by Hudson and others, including I think Karen Rosenloff, looking at total column ozone levels. They noticed that the boundary between the lower ozone tropics and the higher ozone exotropics had moved poleward in recent decades. This sparked like a flurry of activity using a variety of tools and data sets, most of which confirmed that the circulation or chemistry or radiation patterns were indeed shifting poleward, but at rates differing by an order of magnitude. And Diane Seidel summarized these pretty neatly in this figure from her seminal 2007 paper. And later, Diane Seidel with Sean Davis, Thomas Berner, and Lorenzo Polvani convened a Chapman conference in Santa Fe dealing with the width of the tropics, including the climate variations and their impacts. And in spite of years of work documenting and diagnosing the widening of the tropics, when a science writer who was in attendance asked us all, "Can you say for sure that the tropics have widened because of global warming?" they were basically met with crickets. And following the meeting, the next year, this paper came out in Nature, which kind of summed up the attitude pretty well, the mystery of the expanding tropics. It actually mentioned the meeting, and it quoted Diane Seidel saying, "We're at a stage where we recognize the problem is more complex than we originally thought. I think originally we were more confident that this was a result of anthropogenic forcings than we are now." So there were some things that we agreed upon. We agreed that a metrics working group was needed after this meeting. It seems like every few publications, a new metric is introduced to analyze some aspect of the tropics or the widening tropics. And some new methodology is presented along with it. Also, we agreed that regional impacts were woefully poorly understood and poorly represented at the meeting. And I think part of this is probably because of a disconnect between widening theory, which applies on the global level, and then widening impacts, which are experienced at a regional level. So we did form a working group the following year, but with a broader focus than just the metrics alone. Kevin and I are the co-chairs, but Sean Davis has been closely involved in a lot of the planning of the group. He also chaired a working group specifically on the metric issue. So members who are also a member of his working group, sponsored by the International Space Science Institute, are highlighted in red. Kevin will talk more about that later when he discusses the progress made on the metrics front. So our group has 4 goals, 4 stated goals. The first deals with metrics, like we discussed at the Chapman Conference. The second with variability, which is probably the largest gap in our understanding of the widening tropics as a whole. The third deals with regional impacts, which is an incredibly broad topic covering, desertification, monsoons. And the fourth deals with the broader community coordinating our efforts with other groups. Our senior group members have been particularly helpful with this since they have so many of these connections already. Several are involved with SPARC, for example, with their experience with chemistry, stratospheric processes. To address these goals, the first goal is part of a subgroup led by Sean. Kevin's been leading up the second, and I've been leading up the third. And the group members have been loosely divided up into subgroups for each of those 3 goals, but there's substantial overlap. Many working group members are on email lists for more than one of the subgroups. And our timeline's here. And coming up with this timeline, it's actually hard to believe we've only had 1 workshop so far, because with the ISSI meetings that I put on there for your reference, since there's so much cooperation between the two, between the Bloomington meeting, the ISSI meeting, then the telecons that Kristen helps put together, we've managed to stay pretty well connected. Oh, and also several of us met at AGU, and again this summer at an AMS meeting. But the Bloomington meeting, we took some time for each member to upgrade the rest of the group on their research and how they are contributing to the group. And we divided the talks up loosely by these 3 subgroup focus areas. And then we also had time for each of the groups to break out, to plan, and do even a little analysis. So again, I mentioned the ISSI groups because of the cooperation here, even though they're not official meetings for our group. And so with that timeline, I'm going to go and pass the baton over to Kevin here. He's going to just talk about the progress made for the first 2 subgroups. So off to you, Kevin.
Thanks, Paul. So I'm Kevin Grise from University of Virginia. I'm the other co-chair for the working group. And so as Paul mentioned, we divided our working group into really sort of 3 goals. And so what I'm going to do is I'm going to try to talk through a little of the progress that we've made on the first 2 goals, and then Paul's going to come back and finish and talk about the 3rd goal at the end of the telecon here. So, okay, so I'm going to talk about the metrics part of the goal. And so how do you go about measuring the edge of the tropics? And this is turns out to be quite a problem when you look at the literature. And it's a little bit like people feeling different parts of an elephant, because they're all looking at some area that's around 30 degrees latitude that has slightly different characteristics and trying to understand whether that's expanding poleward or not. So some people are very focused on what's going on in the upper troposphere, so they'll look at changes in tropopause height between higher tropopauses in the tropics and lower tropopauses in the extratropics. Others have looked at sort of this dry region where the outgoing long-wave radiation to space is substantially higher, where there's fewer clouds, to try to quantify sort of this subtropical dry region. People look at precipitation, various aspects of the wind field, the surface wind field, the upper tropospheric wind field, also things like sea level pressure. So there's a wide variety of different metrics that people have used to quantify the edges of the tropics. And let's see here. Okay. And so depending on the metric that you use, you get wide varieties of different rates of widening. So this figure here is from a review paper by Thomas Berner. And this figure, I think, is actually taken from the last IPCC report. And so each color here is a different metric. So you can see ozone, jet stream, stream function, tropopause, OLR. And you can see that depending on the metric and depending on the hemisphere, you either get small rates of widening or very large rates. And some of these rates of expansion are on the order of about 2 degrees of latitude per decade, which is quite high and much larger than anything that a climate model would indicate. And this is particularly problematic when you're trying to understand what's going on when some metrics give you large rates of expansion and other metrics don't really show much of any expansion. And so we felt, as Paul mentioned, that as a working group, we need to provide some sort of a list of metrics that, in a sense, we recommend that you use. Because many of these metrics, different authors find different ways to measure the edge of the tropics, and they have a purpose for doing that. But many of these metrics are actually duplicates of one another and basically are highly correlated with one another. Others are very difficult to calculate. They're error-prone, and there's substantial errors in calculating trends with them. And so what we'd like to do is provide a recommended list of these metrics that people, particularly people that aren't as familiar with sort of the large-scale general circulation literature, if they want to correlate sort of what they're looking at with changes in the general circulation, using our metrics might be a good sort of resource for them. And so as I'll talk about in a minute, we're going to be providing some code and also some technical documentation to help people calculate these metrics. So I'll mention that in just a second. As Paul mentioned, there's this sort of separate group that was formed after the AGU Chapman meeting in 2015. And the story is basically that after that meeting, we felt like we needed a working group to deal with this metrics issue. And so, Paul and I put in a proposal to US CLIVAR, and Sean Davis put in a proposal to this International Space Science Institute. And so they turned out they were both funded. And so it gives us an opportunity to sort of have a collaboration between both of these groups working on the same thing. And so you can see, as Paul mentioned, many of the same members are in sort of both groups. We had a meeting in Bern with the ISSI group that Sean led in March 2017, and we'll have another meeting next year in June to conclude that working group. So because of sort of that we've had several meetings on this metrics issue, I think that it's some of the more mature of these goals that our working group has stated thus far. And so there's already been several papers by working group members that are highly relevant to some of our stated goals in the working groups. And so the first several papers, one by Ari Solomon in 2016 and one by Nick Davis and Thomas Berner earlier this year, have done a lot to sort of deal with this issue of duplication across metrics. And so I know these figures are confusing, but basically the moral of the story of these figures is that the lower halves of these figures are mainly red. And what this means is that these lower tropospheric metrics, things like lower tropospheric wind, sea level pressure, the stream functions of the Hadley cell, are highly correlated with one another. And then the upper tropospheric metrics, so things like the upper tropospheric jets, outgoing long-wave radiation, the tropopause height, are very poorly correlated with these lower tropospheric metrics. And so what this means is that if you care about surface impacts, you should probably be using one of these more lower tropospheric metrics that are correlated with things like precipitation and sea level pressure. And the reason, if you're not familiar with this body of literature, the reason that these upper tropospheric metrics are appealing is they allow somewhat of a reanalysis independent method of understanding whether the circulation is expanding poleward or not. And so, for example, you can use pure radiosonde data to determine whether the tropopause heights are changing in the subtropics. You can use satellite radiances to determine whether the OLR field is changing, right? And so what we'd like to do is find some sort of a metric with those fields that you can use that would be correlated with surface impacts. And that's some of the discussion that we had in the meeting in Bern, the ISSI meeting this past March. Okay, and as I mentioned earlier, sort of a tangible or something that's I think hopefully will be useful to the community aspect of the working group is that Ori Adam, who's a member of both working groups, has been developing this MATLAB Python code package. And this is currently being beta tested by working group members. And the idea is that probably sometime next year this will become publicly available in an effort to hopefully standardize calculation of these metrics. And so we'll have code that you can download, open source code, to calculate various changes in the general circulation, particularly dealing with circulation expansion. We'll also probably have pre-calculated time series from common reanalysis products that people can just download. And the idea is to prevent some of the error and also duplication in calculating these metrics that has been done sort of in the past. And so we'll have a technical paper, either a white paper or a published paper associated with that code. And we're not saying that we as a working group have the perfect answer, that we're necessarily define the best ways of sort of measuring changes in the general circulation. But what we're saying is that if you develop a new metric, we would like you to correlate with these existing metrics so we understand what it means and the added value that it brings to the community. And so that's hopefully sort of a tangible aspect that we hope will be continuing even after the lifetime of the working group. That's sort of a useful resource for people to use when dealing with these issues of general circulation changes in the observations and in global climate models. Okay. So that's the first sort of aspect of the working group, and I think it's really the more mature aspect, what we've made the most progress on. So this second issue is the one that I'm sort of technically in charge of, and that's this issue that Paul mentioned at the beginning, is the recent tropical expansion due to natural variability, or is it due to anthropogenic forcing? And I would say probably if you talk to somebody 5 or 10 years ago, the general consensus in sort of the literature was that the rate at which the tropics are expanding is much larger than that predicted by global climate models. And this is certainly true when you compare the multi-model mean of sort of the historical runs of CMIP models with the observed trends from reanalysis data. But I think with the advent of the NCAR large ensemble and a lot of these sort of papers that have focused on natural variability in recent years, it's becoming realized that comparing the multi-model mean with the observations is maybe not necessarily the best way to sort of understand model performance. And so I can go back to another figure from Nick's paper from earlier this year. And this is a somewhat confusing figure, but just focus on, for now, just focus on these black dots, which are different trends in sort of the edges of the tropics over the historical period from global climate models. And then these colored dots over here are from reanalysis products. And the take-home message here is really that there is, in fact, when you compare individual realizations with the individual realizations from reanalysis, that there is, in fact, depending on one of these 6 metrics, substantial overlap between sort of the model trends and the observed trends in each one of these different metrics. And while there might be a couple of outliers where the reanalysis is getting a much larger rate of expansion than the models are getting, in general, I think that there is quite a bit of overlap between the models and the observations in terms of these trends. And so if you look through the literature, there's been a number of different papers that have argued, what is causing the recent expansion in the tropics? What is causing sort of the poleward edges of the Hadley circulation to shift poleward? And so greenhouse warming temperatures, increasing greenhouse gases, obviously, but there's also been studies that have looked at the roles of aerosols, of stratospheric ozone depletion in the southern hemisphere, and sort of the big one that I think has come out in the last 3 or 4 years is really the role of this Pacific change in phase of the Pacific decadal oscillation, particularly in the northern hemisphere. And I think as I'll get into in a minute, I think that the role of natural variability has become more dominant, or sort of amongst people that have thought about this, sort of that in terms of the recent tropical expansion, I think the role of natural variability is thought to be particularly important, whereas maybe 5 to 10 years ago it wasn't. But generally there's a lack of consensus in these studies. So as a working group, what we'd like to do is write somewhat of some short synthesis or review paper dealing with some of these questions. So do climate models have a realistic representation of tropical width variability? What is the primary cause of recent tropical expansion over the last several decades? That's a tough question to answer, but we can at least try to make some stabs at that. And then maybe an interesting question is, when would we expect forced tropical expansion to emerge from natural variability in the future? And so quickly, I want to show one result from another working group member, Bob Allen, who has a new paper out this year. And so this is an interesting analysis. He's done a kind of exhaustive suite of simulations with the NCAR CAM5 model. And so over here, these are trends in the Hadley cell edge based on the mean reanalysis stream function. These are estimates from reanalysis in the northern hemisphere and in the southern hemisphere over the period 1979 to 2014. These are model simulations with what he calls the forced SST trend. So this is the CMIP historical run multi-model mean SST trend. And the point here is that sort of this warming SST trend is really not sufficient to explain the magnitude of the observed expansion that we see in reanalysis data. And so he's run 10 ensemble members here. But then what he does is subtract the forced trend from the total observed trend to get what he calls the unforced trend, which is very much sort of negative PDO pattern. So a switch from the warm phase of the PDO in the 80s and 90s to a cooler phase in the 2000s. And when you force the model with the PDO-like SSTs, suddenly you get much higher rates of expansion, at least in some ensemble members in the northern hemisphere. In the southern hemisphere, there's still not that much expansion. And other studies, including Darren Waugh's paper a couple years ago, have argued that ozone depletion is likely responsible for a lot of the southern hemisphere expansion. But in terms of Bob Allen's paper, I think the take-home message is written here basically that there's the bulk of the recent widening is due to this natural variability, likely due to this PDO-type variability. Okay, so I've covered the first two aspects of the working group. In the last couple of minutes here, I'm going to turn it back over to Paul, who's going to talk about this third aspect of the working group in terms of the regional aspects.
Thank you, Kevin. Yeah, so from Kevin's slides, you saw that there are these distinct signatures, so the variability, distinct spatial signatures from interannual variability and the force response. And that kind of leads us to this third goal, or this third focus area, which is on the regional impacts of tropical widening. Perhaps the first challenge with this group is narrowing the focus. For different longitudes, the tropics can mean different things. In some areas, it's basically the width of the precipitation belt that people are concerned with. But for the purpose of this subgroup, we decided to focus on the latitudinal expansion of subtropical dry belts rather than the expansion or shift of the ITCZ. Essentially, we're focusing on the aspects of the widening tropics that are related to the subsidence on either side of the equator. So this is from work with some of our group members as co-authors. For a group was formed. Not all the metrics that apply in the zonal mean work in the regional mean. So one challenge is just deciding how to measure regional change. Plus, observing regional change is complicated even more by inhomogeneity in the instrumentation. There are some places where a given metric may be more useful in other places simply because you have the capability to measure it. Finally, the same metric troubles that apply in the zonal mean also apply in the regional mean, sometimes worse. So in this figure from Chen et al., If you look at the first column of both panels, Z and C, that's basically the zonal mean cell edge. And the red and the blue bars are using a similar metric. This is outgoing long-wave radiation from outer space, but it's most of the highest values of outgoing long-wave radiation are coming from the tropics, with values that taper off towards the poles. And you can use about 240 or 250 watts per meter squared as a cutoff for the edge of the tropics. And for the zonal mean cell, they both seem to do pretty well, but each column after that represents a different region. And for some regions, like the Western Pacific, the fourth one over, the 240 watts per meter squared, which is a reasonable estimate of the width of the tropics, shows significant widening, or at least over the northern hemisphere. But the 250 watts per meter squared shows that the Hadley cell is not widening at all. So the same problems that exist for metrics on the global scale also apply at the regional scale. Another tricky thing is when you're deciding how to measure regional change, you need to decide what kind of regional changes you're talking about when you say the tropics are widening. Because depending on the metric you choose, so here's some of that bleed over between the different groups, depending on the metric you choose for the widening as a whole, you're going to get a different contribution from the different regions. So this is from Amanda Maycock, actually at the ISSI meeting, but I thought it was really interesting for my focus area. You've got JJA on the left, DJF on the right, and each row is the correlation between precipitation and some different metric for the width of the tropics, whether that's the stream function, it's the top row, the strongest downwelling, strongest downward velocities in the subtropics, or the bottom one is the separation of the subtropical jets. And broadly speaking, the regional patterns are pretty similar, but you can spot differences in the regional response depending on which zonal mean metric you pick. So when we start looking at the regional response to Hadley cell widening, we have to be sure what we mean by, or tropical widening, we have to know what we mean by tropical widening, and because that will affect the regions that we focus on. There are also regional factors that come into play in addition to the factors, like maybe global average, equator to pole temperature gradient, vertical stability, and things that affect the overturning circulation as a whole. You also have tropical mid-latitude connections. You can have influences from the extratropics to the tropics that affect one region fairly locally. You can also have zonal dynamics within the tropics that augment Hadley dynamics. Chris Granauskas and Carolyn Umenhofer have a neat paper where they show that regionally, in addition to the overturning that you would expect from the Hadley cell itself, you have this vertical wind shear that's in the same sense. It's contributed to by east-west temperature gradients on coastlines that run north or south in the subtropics. And these can be pretty strong, so that augments the Hadley cell dynamics at a regional level. Also, in addition to the changing circulation, you just have thermodynamics in a warming climate. On a large, zonal mean or global scale, thermodynamics are king. And so while the atmosphere warms and it can hold more moisture where there's more moisture available, relative humidities look like they're going to stay pretty similar as things warm up. But over land, where it's moisture starved with increasing temperatures, even in many regions where you have increasing precipitation, you still have an increased aridity. And so from an impact perspective, a lot of regions in the subtropics are going to experience a widening of these climate zones associated with the tropics or subtropics, even if the circulation itself doesn't change. So there's a thermodynamic component to this as well. But getting back to the circulation, this recent paper, 2017, Xiaoku Son's one of our group members, they looked at the regional circulation response to various forcings. So they looked at natural forcings, anthropogenic forcings, and they separate out greenhouse gas forcings and C and natural forcings at the bottom. And you can actually, so you can see a different regional response to each of the different forcings. Even for forcings where the zonal mean response are pretty similar, the regional response could be quite different. And there's more work going on this by Kevin and others using this regional signature of different forcings to improve detection and attribution studies to help understand how much of the observed Hadley cell widening or the observed tropical widening is forced and how much of it's natural variability. So our working group, we want to document these regional impacts associated with tropical widening due to anthropogenic forcings, separate from variability. And also, we want to isolate regions that are likely to be impacted by globally widening tropical overturning circulation. This is a thing that we're producing metrics for, so we want to understand the impacts as these circulation patterns widening, as well as thermodynamics. This is some more work myself and some others have. So a couple of years back, there was a paper where they actually basically divide up the Hadley cell into its longitudinal components. You take the vertical motion in the atmosphere, which involves upward motion involves convergence below and divergence aloft. You can uniquely separate the vertical motion into the part that's due to meridional wind shear and the part that's due to zonal convergence. And on this left panel here, we're looking at the stream function. Basically, we're looking at the 500 millibar stream function, but instead of in the zonal mean, we're looking at region by region. So the gray contours, you could say, represent the wintertime Hadley cell circulation, or the wintertime circulation that's moving northward aloft and southward below. And this gives you a good impression about the regional variability of the Hadley cell. Typically, people have looked at sea level pressure climatology and sea level pressure changes, and we talk a lot about centers of action. And you can see on the figure on the right, during DJF, you have these centers of action mostly focused on ocean basins, although you also have the Asian monsoons. But when you look at a map and you talk about impacts, people are going to be experiencing a lot of the impacts over land. And we talk about the ITCZ a lot because that's what gives you rainforests, and you have the dry belt on your side. And if you look at the this sort of Hadley cell decomposition, it gives you a pretty good indication of the Hadley cell strength over land in the deep tropics, and it lines up pretty well with what you can see even just looking at a picture of the Earth from space and looking where the deserts and rainforests are. So it's an interesting new metric. It looks like it's going to be a way for us to improve our study of the impacts, not just looking at sea level pressure, but also looking at this sort of decomposed Hadley circulation. So we're going to be looking at the sea level pressure, this decomposed circulation, precipitation, temperature, and that's where our subgroup is right now. So in the future, we have another telecon coming up in a couple of weeks here, and at this telecon, we're planning to update group members on the progress made by different groups, particularly by the first group for any members of our working group who aren't in ISSI as well, and also to encourage group members to bring their analysis, bring their figures to the workshop coming up in Boulder this October. We'll also be giving a presentation to NCAR and UCAR there, and we see that workshop as kind of a chance for us to plan the papers that we plan to write for each of the three subgroups in the following year, and to have some preliminary analyses. Basically, you bring these figures because this is the kind of analysis we're going to do in 2018. And then Kevin and I are chairing an AMS session in January. That'll give us a chance to get some feedback and input from the broader community, and make sure that we put our papers in a good context here. And they'll be working on the synthesis paper throughout 2018 with one more ISSI meeting in June. And then as we're wrapping things up, we'll have an AGU meeting in December where we can disseminate our results and start thinking about the next step and following up. So that's where we stand right now. Thank you again for taking the time to meet with us today, And I guess now Kristen will open these up to questions.